Hi, I'm Ivan Hyde with Coking.com, and we are on site at the factory floor with Luke Just from ValvTechnologies, and he's going to give us a rundown today about their valves, some of the cool design features, the zero leakage concept. But Luke, just introduce yourself briefly for our audience, please.
Yeah, hi everyone. So my name is Luke Just. I am the industry director for oil and gas here at ValvTechnologies, and I've been here 5 years now.
Okay, perfect. Thanks, Luke. So what do you have to show us today? What is this beautiful coker valve that you have behind us?
Yeah, so as Evan mentions, here's one of our coker valves. This is showing a little bit of our general configuration with the purging setup and the valves.
So one of the things that we're here to talk about today is zero leakage, right? And I think this is something that you've been trying to use as a standard for safety. And of course, we're all about safety in delayed coking world. So how does this zero leakage standard work compared to sort of the normal API standards?
Yeah, so zero leakage, there's a lot of different terms, nomenclature, industry standards that can be used, tight shutoff, bubble tight, all of these describe terms, but do have an allowable leakage. And what we do here at ValvTechnologies is provide a valve with a true zero leakage. That is zero bubbles, zero drops.
Okay. And you mentioned ahead of this, you do this under a vacuum even.
Yeah.
Like normally you would do it sort of like pressurized, and you sort of go maybe a step beyond that?
Correct. So as every valve goes through the manufacturing process, after lapping, we will do a vacuum test where the ball sits on the integral seat, similar to this configuration here. It'll sit on...
Let's grab this little guy. So
it'll sit on a vacuum underneath, just testing to ensure that we've achieved that perfect lap, that mate of the ball to the end cap, ensuring zero leakage.
Well, I'd encourage the viewers to step back and watch one of our other videos about the integral seat where we talk about this arrangement separately, but here we're talking about zero leakage. So let's move back to the bigger valve, and let's just say here we have the valve here, and this is the integral seat side, and then we have the purge steams coming on the other side and moving around. And this is something that coming out of the factory, it's all super tip-top tight, right?
Correct. Yeah, so again, through our lapping, through our grinding processes, the ball will get mate lapped to the end cap, ensuring that zero leakage through the bubble tight, through our FAT procedures, and every valve that goes out will be to the zero leakage.
Okay.
Yeah. The purging just helps to maintain that throughout operation.
So we're all familiar in coker land about different purging arrangements. Maybe we'll just walk around to the other side just quickly to show this purging arrangement, where I think this is where some of the magic happens. We're all familiar with, utilizing steam. Steam is how these valves live or die. You got to have reliable steam to keep them reliable over long time scales. These purge ports, if there's zero leakage, how will the flow move through this system?
Yeah, so our purging configuration, a continuous configuration, we have these three inlets on the one side of the valve where the steam is flowing through, and we have the return on the back side. And one of the benefits that comes out of the zero leakage is that there is zero steam loss across the valve when the valve is in the closed position. So the cavity is still being purged. It's still moving back to the upstream side of the valve, but there will be zero loss of steam across the valve to the downstream side across the integral seat.
Into the process. So
Correct.
I think that's one of the things that's interesting about this particular layout. So in coker land, we always use two valves, right? Double block and bleed. So we would have this valve and then its mirror image next door, right? So these purges would be going in and they would be coming out the other side into the spool, right?
Correct. And this actually aids operators in their blocking steam, right? When you have these different locations in the coker where you utilize the blocking steam, as that steam is flowing back into the upstream side, the high pressure end of the valve, then you are actually achieving that blocking steam at a faster pace, thereby steam savings.
And so not only would you have the blocking steam on the valve itself, you kind of have that one on the spool.
Correct.
And everything, when it all comes together, double block, everything comes up to pressure, you should have no steam consumption.
Correct.
Right.
Exactly. You'll have zero loss of steam across the end cap, no loss of steam. And we actually have examples over time where we've been able to maintain this leakage requirement. Operators that show the torque being used in the valve has been maintained over a long period of time.
Yeah, normally we would expect some, hopefully modest accumulation in torque over time. You're saying that, by using this integral seat, by using this, lapping zero leakage concept, that you're able to sort of maintain the health and integrity of that system over long time scales?
Exactly. Because of the lapping, because of the increased surface area contact between the ball and the end cap, we are able to help ensure that over the life of the valve, it's going to maintain that zero leakage for a longer period of time.
Okay, well, I'm all about zero leakage for safety. I think everyone else in the audience would agree. So thank you, Luke, for explaining this to our audience, and hopefully you learned something. And check back to the rest of our videos and join us at the channel to learn more about all things delayed coking. So thanks a lot for viewing.
Thanks, Evan.